inverses. Okay, this is a topic that we're going to cover today. First of all, the basic matrix operations consist of real-life example, determine dimensions or the size of a matrix, matrix addition, matrix subtraction, a scalar multiplication, and application problems. And then for the second part is going to be matrix products and inverse, which consists of matrix multiplication, identity matrix, and inverse matrix. Okay, so let's start with the first topic, which is matrices. Matrices are important in the fields of management, natural science, engineering, and social science as a way to organize data. Okay, here's an example. Example number 1, furniture manufacturing. This reads as the Easy Life Company manufactures sofa sets, and armchairs in 3 models, models A, B, and C. The company has regional warehouses in New York, Chicago, and San Francisco. In its August shipment, the company sends 10 Model A sofas, 12 Model B sofas, and 5 Model C sofas, and 15 Model A chairs, 20 Model B chairs, and 8 Model C chairs to each warehouse. So how can we organize this data? Okay, it can be done like in 2 to 3 ways. The first way is by a list, right? For example, the sofas consist of 10 Model A, 12 Model B, and 5 Model C, right, from the given information on top. And for the chairs, it's going to be 15 Model A, 20 Model B, and 8 Model C. That's one way to organize it. Another way is called the tabulate. We might tabulate the data in this form, right? On top, horizontal are the models, right? Models A, B, and C, and vertically are the equipment, which are the sofa and the chair, right? So there's 10 Model A. For the sofas, there's 10 Model A, 12 Model B, and 5 Model C. In a similar fashion, for the chair, we have 15 Model A, 20 Model B, and 8 Model C. Or it can be done as a matrix. Okay, let's call this matrix A. Matrix M for the model. And here we go. That's in matrix form. The rows refer to the furniture, which is the sofas and the chairs, and the columns are the models A, B, and C. Okay, so we're gonna more or less for this section or for the chapter is more or less gonna be, well, it is gonna be as a matrix. Okay, this is an example of matrices in the real life world. Now, matrices, for example, if this is matrix A, right, and this is matrix B, for example, matrices are denoted by capital letters. And these are called the entries, which are denoted by lowercase letters. Okay, again, like I put here, the uppercase letters are used to name matrices. Example, matrix A and matrix B. And lowercase letters are used to name the elements of the matrix. Example, element A for matrix A, and element B, lowercase a and lowercase b for matrix A and B. Now, matrix are rows by columns. First is going to be the rows and then the columns. So this is called the position of an element. For example, A11 stands for matrix A, right? This is element A. This is the first row, first column. That's a position. Now again, is row 1, column 1. Lowercase a14 means row 1, column 4. A23 means row 2, column 3. Okay, for example, right? Say this is an example here for you guys to know how to know the positions of an element. For example, if I tell you what does A13 stand, what's the value or the element for A13, the position, right? So it's going to be A13 means the first row, which means first row, and third column, so the position will be number 3. A24. it stands for the second row, fourth column, so second row, and fourth column will be the 8. Okay? Now, matrix dimensions. This is called the size of a matrix. It's going to be rows by columns. The number of rows X times the number of columns. For example, right? This is a 2 by 4 matrix because you have 2 rows and you have 4 columns. Example 2. Determine the dimension of the matrices. Right? So for this first matrix on the left, it's going to be a 3 by 3, right? Because we have 3 rows, 1, 2, 3, and 3 columns. So it's a 3 by 3 matrix. The matrix in the middle is going to be a 3 by 1 because we have 3 rows and we have 1 column. And the matrix on the far right is going to be, right, we have 1 row and 3 columns. So it's going to be a 1 by 3. This is how you figure the size of a matrix. And this is crucial, guys, when you add, subtract, or multiply matrices. Now, determine the order of the matrix, right? So how many rows? We got 1, 2, 3, 4. So it's going to be a 4 by the columns. We got 2 columns. So it's going to be a 4 by 2. That's the answer. Okay. Now comes matrix operations. Right? In order to add or subtract matrices, the matrix must be the same size. They must be the same size. If not, it cannot be done. Okay, this is matrix A plus B, right? So this is how you're going to add them, right? So you can add the same position, guys, but on matrix A and on matrix B. So it's going to be A11 plus B11. And then A12 plus B12. And it's going to go all the way to the first to the first row times a number of columns, right? Because this can go forever, right? Or not forever, but it can go for any number of columns, right? So it could be A13 plus B13, right, and so forth. And same thing, right? It's going to be A21 plus B21, A22 plus B22, right, and so forth. It goes all the way until the end. That's why they have to be the same size when you're going to add them or subtract them. Okay, let's try some examples. And also, right, so this is like the definition. At times, the definition sounds harder than what it really is. Okay, but anyway, here's the matrix addition definition. The sum of two m by n matrices. The m means the number of rows times the number of columns, right, on matrix X. And Y is a n by n matrix, right, which they have the same, the same size of matrix, is X plus Y, in which each element is the sum of the corresponding elements of X and Y. Like I said, this is a little bit hard to understand for the students to understand it, but by doing the example, we can do an example to describe the definition. Okay, so let's do examples on the next page. Also, for the difference, it's the same way. For the difference, right, if you have A minus B, it's going to be A11 minus B11, A12 minus B12, and so forth. Example, right? So we're gonna do operations on matrices. The first thing we gotta do is to make sure that we can actually do the operation. So, for example, remember that the matrices must be the same size. So matrix A is a 2 by 3 matrix. Matrix B is a 2 by 3. Matrix C is a 2 by 2. And matrix D is also a 2 by 2. So can we do A plus B? Sure we can, right? Because A and B are the same size. So here's how we can do an example to describe the definition. Right? So it's going to be 1 plus 8, right? Same location. Negative 3 plus 0. 2 plus 1. 2 plus negative 1. 2 plus 3. And negative 1 plus 4. Right? So it's going to give us 9. Negative 3. 3. 1. 5. And 3. That's my result. Now, can we do C plus D? Sure we can, right? Because C is a 2 by 2 and D is a 2 by 2. So follow the same concept, right? So it's going to be 5 plus 2, 1 plus negative 1, negative 4 plus 9, and 3 plus negative 7. Hey guys, we can skip this part here, guys. If you want to, right, you can go straight to the answer, for example, right? This is, this part here is to show you what's taking place, but you can go like this, guys. What's 5 plus 2? It's going to be 7. 1 plus negative 1 is going to be 0. Negative 4 plus 9 is going to give us 5. 3 plus negative 7 will give us negative 4. Right? Again, you can go straight from the C plus D, right to the answer. This middle part is just to show you what's taking place. Okay, but you can do it any way you want, but just do it correctly. Now, can we do A plus C? If you notice, A plus C cannot be done. Why? Because matrix A is a 2 by 3 and matrix C is a 2 by 2. 2 by 3 and 2 by 2 are not the same size, so it's not possible. Okay. Now comes the subtraction. So again, right, we're going to do, these are the same matrix as before, but instead of adding, we're going to subtract them. A minus B, right? So it's going to be 1 minus 8, negative 3 minus 0, 2 minus 1, 2 minus negative 1, 2 minus 3, and negative 1 minus 4. So it's going to give us, right? It's going to give us negative 7, negative 3, positive 1, positive 3, negative 1, and negative 5. That's your result. Can we do C minus D? Again, sure we can, right? Because they're the same size. It's going to be 5 minus 2, 1 minus negative 1, negative 4 minus 9, 3 minus negative 7. So 5 minus 2 is going to give us 3. 1 minus negative 1 will give us 2. Negative 4 minus 9 will give us negative 13. And 3 minus negative 7 will give us positive 10. So this is my result. Can we do A minus C? Again, this is not possible because matrix A is a 2 by 3 and matrix C is a 2 by 2. So this is not possible because they're not the same size. Okay. Now let's do the scalar multiplication. Okay. This is a product of a scalar K. And A in matrix X is a matrix Kx with which each element is K times the corresponding element of X. Again, it's better to do an example than to read the definition, okay? But here's what the definition means. Here they give us a matrix X, right? Matrix X is a 2 by 3 matrix, and the elements are 2, 0, 5, 4, negative 2, negative 3. So if I want you to find 6x means 6 times matrix X means that you're going to multiply 6 times every element and X. It's going to be 6 times 2, 6 times 0, 6 times 5, 6 times 4, 6 times negative 2, and 6 times negative 3. So the result will be 12, 0, 30, 24, negative 12, and negative 18. That's my result. I want you to find minus X, right? Or isn't there like a negative 1 there, guys, right? There's an invisible negative 1 there, right? So we can say negative 1 times X, which means I'm going to multiply negative 1 times every element in matrix X, which will give us negative 2, 0, negative 5, negative 4, positive 2, and positive 3. That's my result. Okay, now matrix operations, okay, continues. This is like 3 parts here, right? The first part, they want you to find negative 4a. Second part, or number 2, 5b. And then on the third part, part 3, right, is negative 4a plus 5b. Okay, so let's first start by doing -4 times matrix A, which would be -4 times -2, 0, 5, and 3. It will give us -4 times -2, -4 times 0, -4 times 5, and -4 times 3. But if you want, guys, you can go straight from the original problem, guys, straight to the answer. Again, we skipped this middle step, but this is just to show you what's taking place. -4 times -2 will give us 8. -4 times 0 will give us 0. -4 times 5 will give us -20. -4 times 3 will give us -12. Now, I put these answers in blue because it serves a purpose. Okay, when we do number 3, I believe number 2, I'm going to do the answers in red. Okay, but first let's do 5 times matrix B. There's matrix B, right? 0, 2, 4, -6. So again, 5 times 0, 5 times 2, 5 times 4, and 5 times -6. So here's my result. Will give us 0, will give us 10, will give us 20, will give us -30. So for part 3, right, for number 3, we're going to add -4a plus 5b, and I already have the answers here for -4a and for positive 5b. So all we do is we're going to add them. Right, there's my -4a plus there's my 5b. Now we're going to do what we did in the previous slide. It's going to be 8 plus 0, 0 plus 10, -20 plus 20, and -12 plus -30. My result will be 8, 10, 0, and -42. There's my result. Okay, now, you guys remember the problem that we did the first example? Now here's how we can apply matrix operations on this example here. Okay, I said recall example 1, right? The example. So I'm not going to read it. I'm not going to read it right. This is what we have here. The only thing that I'm going to do, guys, is read this place here. Okay, let's see here. Right, this first part comes from slide number 1. Now this here is extra, guys, right? What here it says. It says, let me read from the beginning. Okay, the Easy Life company manufactures sofas and armchairs in 3 models: models A, B, and C. The company has regional warehouse in New York, Chicago, and San Francisco. In this August shipment, the company sends 10 model A sofas, 12 model B sofas, and 5 model C sofas, right, which is a 10, 12, and 5. And then it sends 15 model A chairs, right, so 15 for the chairs, 20, and 8. Here are the models. Now, during August, the Chicago warehouse of the Easy company, shipped out the following numbers of each model, which the entries in the matrix have the same meaning as given earlier. So Chicago shipped out 5. This is for the sofas, right? 5 model A sofas, 10 model B, and 3 model C. And for the chair, they shipped out 13 model A, 12 model B, and 8 model C. And the letter uppercase K represents the shipment that's going to go out. So what was the Chicago's warehouse inventory at the end of September, taking into account only the number of items received and sent out for the month? Okay. So here we go, guys. Right. So this is for the C stands for Chicago. So it's going to give us C minus K will give us the inventory at the end of September. So the C, guys, right? So this is what they received was 10, 12, 5, 15, 20, and 8. And the K is what went out, right? Which is the 5, 10, 3, 13, 12, and 8. So C minus K will give us 10 minus 5, right? Which will give us 5. 12 minus 10, which will give us 2. 5 minus 3, which will give us 2. 10 minus 13 will give us 2. And 20 minus 12 will give us 8. And 8 minus 8 will give us 0. Which means, right? Let me go back real quick. Which means, right? Remember, guys, so there were the first row are the sulfas, right? Which after the transaction, there were 5 model A, 2 model B, and 2 model C left for the chairs. For the sulfas. For the chairs, there were left 2 model A, 8 model B, and there were none left for the model C. This is the inventory after the transaction. Okay, now matrix product. Hey guys, this is very important here, guys. Write down. That's why I put it in red. Very important information. Multiplication of matrices can only be done under the following conditions. Right? Say matrix A, the size is m by n, or m times n. Matrix B must also be m by p, right? Which means the two numbers in the middle, right? They must be the same. If they're the same, then the operation can be done. Must match. And the answer will be the outer numbers. Will be m by p. For example, if the size of matrix A is a 2 by 3, then matrix B must be a 3 by something. A 3 by any number. This can be a 1, a 2, or a 3. This can be whatever it is, right? But the 2 in the middle must match. And the answer will be a 2 by whatever the number is. That'll be the solution. Okay. Example 7. Give the following matrices and state whether the matrices can be multiplied. Matrix A, matrix B, and matrix C. Matrix A is a 2 by 3. Matrix B is a 2 by 2. And matrix C is a 3 by 2. Now, can we multiply A times B, B times A, or A times C? Well, let's find out. A times B, right? If you notice, this is matrix A is a 2 by 3, matrix B is a 2 by 2. So the two in the middle, the two numbers in the middle, they're not the same. So this is not possible. No match, so not possible. Cannot multiply. How about if we reverse it, right? This is A times B. How about if we do B times A? B is a 2 by 2. A is a 2 by 3. Now we have a match. So yes, it can be done. And what's my solution? The answer will be a 2 by 3 matrix. Okay. How about A times C? A is a 2 by 3 and C is a 3 by 2. So yes, it can be done. A match, yes, it can. And the solution will be a 2 by 2 matrix. Okay. Let's do some examples here. Example 8. Right? So let's do B times A. Right? Again, this is a match, so it's a 2 by 3. So this requires a few steps. I think it'll be like 6 steps here. Step 1, right? I have to multiply every row times every column. That's why I color-coded it, because the first thing, we're going to multiply the first row times the first column. Okay? Example. What's 1 times 2? Right? Plus 0 times 4. This will give us 2 plus 0. The answer is 2. So the 2 goes in the first slot. Now step 2. Right? I should need to have the same row, because I need to multiply the first row times every column. So the next one will be column 2, which will be in red. Right? I already did the first column, which was step 1. Now step 2 is going to be 1 times 0 plus 0 times negative 2. The answer will be 0. So the 0 goes on the first row, second column. Now let's do step 3. So step 3, right, what you have to do is row 1 times column 3. And column 3 will be in red now. So 1 times 5 plus 0 times negative 3. And the answer will be 5. So the 5 goes on the on the first row, third column. Right? Since we're done, right, with the first row times every column, now step 4 means Now we're gonna do row 2. Row 2 times every column. So let's start with row 2 times column 1. So 4 times 2 is 8. Negative 2 times 4 is negative 8. So we add them, it's going to give us 0. The 0 goes on the second row, first column. Now step 5. So it'll be the second row times the second column. 4 times 0 is 0. Negative 2 times negative 2 is 4. So 0 plus 4 will give us 4. So the 4 goes on the second row, second column. And finally, we got the last step, which will be the second row times the last column, which is column 3. 4 times 5 plus negative 2 times negative 3 will give us 20 plus 6 will give us 26. And that goes on row 2, column 3. So that's your results. Okay, it doesn't matter. It doesn't matter the size of the matrix. What matters is that if they can be multiplied, all you do is follow the same concept as what I just did. Now comes the identity matrix. Okay, recall from section 1.1 that a real number 1 is the identity element for multiplication of real numbers. For example, for any real number a, right? How can we get a times 1 is the same thing as 1 times a is equal to a. That's why 1 is called the identity element for multiplication. Now in this section, an identity matrix is matrix I. It's defined that has a property similar to those of number 1. Example, if you multiply matrix A times the identity, it's going to give us the identity times matrix A is equal to A. And here the identity, guys, for a 1 by 1 matrix, it's just 1. For a 2 by 2 will be 1, 0, 0, 1. If you notice, all the ones, all these are diagonal. Have to be ones. You see, for a 3 by 3, it's going to be 1, 0, 0, 0, 1, 0, and 0, 0, 1. If you notice, all these diagonally are ones. For a 4 by 4, it's going to be 1, 0, 0, 0, 1, 0, 1, 0, 0. 0, 0, 0, 1, 0, and 0, 0, 0, 1, and so forth. Okay, this is called the identity matrix. Example 9, right? We have matrix A. Matrix A, here's the concept, is A, B, C, and D. Right? The identity matrix, because this is a 2 by 2, is going to be 1, 0, 0, 1. So if I multiply matrix A times the identity, it's going to give us matrix A, right? According to the rules here, to the identity matrix definition. Well, let's prove it to you. Let me prove it to you guys. Right? This is matrix A times the identity. Again, right? It's going to be the first row times every column. So A times 1 plus B times 0. It's going to give us A plus 0 will give us A. So A goes on the first lot, on the first row, first column. Now comes step 2. I'm going to multiply the first row times the second column. A times 0 plus B times 1 is going to give us 0 plus B. So the answer is B, and the B goes on first row, second column. Since there's no more columns to do, right, then we have to go to our next row. So step 3 will be row 2. Right? Row 2 now times column 1. So C times 1 plus D times 0 is going to give us C plus 0 will give us C. And finally, step 4, right, is going to be the second row times the second column. C times 0 plus D times 1 is going to give us 0 plus D. The answer is D. You see, so if we multiply any matrix times its identity, we're going to get the same matrix. Okay, now, the inverse. Recall that for every non-zero real number A, the equation AX equals to 1 has a solution, namely X equals to 1 over A. That's the inverse, 1 over A. And this is a notation, A to a negative 1. Similarly, for a square matrix A, we consider the matrix equation AX equals to the identity. The equation does not always have a solution, but when it does, we have a special terminology of if there is a matrix, the matrix inverse of A, which means A times A inverse is equal to the identity. The inverse A to the -1 is called the inverse matrix. Let me do example number 10 and explain what I just mentioned here for the definition. It says, given matrix A and matrix B as follows. Determine whether B is the inverse of A. How do we do that, guys? If we do the multiplication, it's going to give us the inverse. And there's a way to put this in the calculator, guys, right? But I'm not going to show you how to do that. Okay, maybe if you come to Trans Mountain or maybe go to the tutoring places, they might show you how to put it into the calculator. Okay, but here, guys, I want to show you how to do it by hand. But if we do multiply them, this is what we get, which is identity. But let's do the work here. Oh, no, guys, I didn't do the work. But if you do the work, you will get 1001 if you multiply them out. Okay. Now, they give us a matrix A, right? They want you to find the inverse. So to find the inverse, right, here's what we do. And we're going to do the Gauss-Jordan method, what Mr. Carrizales covered last week, because last week I was out, right? But Mr. Carrizales covered the workshop for me, and he did the Gauss-Jordan method. So here we go, right? So this is the objective, guys. I wanna send the 1001 to the left side, and whatever's on the right is the inverse. Okay, here we go. Right? This is the inverse, right? But how do we get the answer? Here's how. So the first step, right, this has to be a 0 here, where the 2 is. This is considered row 1 and row 2. So I'm going to multiply -2 row 1 and add it to row 2. And, right, row 1 stays the same, and here's my work. -2 row 1 is -2 times 1, -2 times 4, -2 times 1, -2 times 0, right? I'm multiplying -2 times row 1. This is my result. -2, -8, -2, and 0. Where do those numbers come from? If I multiply -2 times 1 will give us -2. If I multiply -2 times 4 will give us -8. -2 times 1 will give us -2. And -2 times 0 will give us 0. Plus row 2. So row 2, all we do is bring it over, right? The 2, 6, 0, 1. Now we add them. So we get 0, -2, -2, 1. This is my new row 2. Now, the one where the 4 is, it's got to be a 0. Right? And also, all these diagonally, these must be 1s, right? But let's wait and do that later. This way, we eliminate all fractions. So my next step is the position of the first row, second column. This has to be a 0. So I'm going to use row 2, right? I'm going to multiply 2 times row 2 and add it to row 1. That way, it guarantees to give me a 0 on the spot right there. And here's my work, right? So we're going to keep row 2, and here's the work. So it's going to give us 2 times 0 will give us 2, will give us 0. 2 times -2 will give us -4. 2 times -2 will give us -4. And 2 times 1 will give us 2. Then we're going to add it to row 1. Row 1, we just bring row 1 over, which is 1, 4, 1, 0. Now we add them. It's going to give us 1, 0, -3, 2. So that's my new row 1. But one thing's missing here. The second row, second column must be a 1. So I'm going to multiply the whole row 2 by -1/2. If I do that, it's going to give us, right, the first row is going to give us 0, 1, -1/2 times -2 will give us 1. -1/2 times 1 will give us -1/2. So this is considered my inverse. The -3, 2, 1, and -1/2 is my inverse. That's your answer. Okay, now, hey guys, this is kind of simple, right? But a simple compared to a 3 by 3 matrix. But if this gives you a hard time to follow, there's an alternative only for a 2 by 2 matrix, and here's the alternative. We're going to be using this formula here to find the inverse. Right, it's going to be 1 over the determinant, which means 1 over A times D minus B times C. And then the A and the D switch places, right? The A and the D switch places, and B and C, you change the signs. So this is the formula, guys, that we're going to be using. Okay? And I believe this is the same problem from before. Okay, now, so the inverse will be 1 over 1 times 6 minus 4 times 2. And then the 1 and the 6, we're going to switch places. And the negative and the 4 and the negative 2 are going to switch signs. For example, right, so it's going to be A times D, which is 1 times 6, right? And then minus 4 times 2. But here, guys, the 1 and the 6, which is the A and the D slots, switch places. And the C and the... Hold on. Hey, let me get this real quick. Oye, ¿qué pasó, José? Oiga, no ven ocupado ahorita, pero véngase para la casa ya, si quiere. O bueno, pues, ando bien ocupado ahorita, no puedo hablar. Okay, bye. Sorry about that, guys. I just have to get that call. Okay. Okay, now, guys, so now, if you notice here, we're going to get negative 1/2, right? Because 1 times 6 is negative 6. I mean, 1 times 6 is 6, and minus 4 times 2 is 8. So 6 minus 8 will give us negative 1/2. So now I'm going to multiply negative 1/2 times every element here. Negative 1 times 6 will give us negative 3. Negative 1 times negative 4 will give us positive 2. Negative 1/2 times negative 2 will give us positive 1. And negative 1/2 times 1 will give us negative 1/2. So this is my inverse, my inverse. Okay, now, but not every time is as easy as the one that we just did. So for example, here, guys, right, they want you to get the inverse of a 3 by 3 matrix. This is as hard as it gets, okay? And here, guys, there's no special formula to get the result. You have to do it this way. Okay, now, right, there's a matrix 1 0 1 0 1, 2 negative 2 negative 1, and 5 0 0. And here's the identity 1 0 0, 0 1 0, and 0 0 1. Now I'm going to do the same thing, right? The Gauss-Jordan method. So this will be my solution here. So this is my inverse right here, guys. Right? This is my inverse on this side. That's the inverse. But how do we get it? Here's how. So this is row 1, row 2, row 3. So the objective is to bring the right side, the identity, to the left side. And if whatever's left on the right side, that's your inverse. Okay? So I guess also Mr. Rosales did the Gauss-Jordan method last week. So this is just expanded from the workshop that we did last week on the Gauss-Jordan method with a 3 by 3 matrix. Okay, now if you recall, guys, from last week, step 1, right? Step 1, we're going to keep row 1. So the 2 and the 5 must be zeros. These two must be zeros. Okay, I'm going to use row 1 to make these two zeros here. So I'm going to multiply negative 2 times row 1 and add it to row 2. Then I'm going to multiply negative 5 row 1 and add it to row 3. And here's my work. Right, so negative 2 row 1 will give us negative 2, 0, negative 2, negative 2, 0, 0. Plus row 2. Row 2, what we do is bring row 2 over. Will give us 0, negative 2, negative 3, negative 2, 1, and 0. That's my new row 2. Now for the second part on step 1, we're going to multiply negative 5 row 1, right? Negative 5 times row 1 will give us negative 5 times 1 will give us negative 5. Negative 5 times 0 will give us 0. Negative 5 times 1 will give us negative 5. Negative 5 times 1 will give us negative 5. And negative 5 times 0, 0 will give us 0, 0. Plus row 3. Row 3, all we do is bring row 3 over. Now we add them. We get 0, 0, negative 5, 0, 1. So that's my new row 3. So we're done with step 1. Remember, guys, step 2 was we had to make these two zeros here and call them 2, right? So these has to be zeros. Since they're already zeros, we're done. So now we got to do step 3. So for step 3, for the 1 is on row 1, column 3, that must be a 0. And also row 2, column 3, where the negative 3 is, that must be a 0. So we're going to be using row 3. So it's going to be 5 times row 1, right? Row 3 plus 5, row 1. Then it's going to be row 3 plus row. It's going to be no here, guys. Right, for the second one, it's going to be I got to multiply row 3 times 3 times negative 3 and add it to 5 row 2, because this is going to give us 15 and negative 15. Here's my work. Row 3, right? So row 3, all we do is bring it over row 3. So plus, right, 5 times row 1 is 5 times row 1 is 1, 0, 1, 1, 0, 0. And we multiply 5 times every element in row 1 is going to give us 5, 0, 5, 5, 5, 0, 0. Here's my result. 5, 0, 0, 0, 0, 1. That's my new row 1. Negative 3, right? Negative 3 times row 3 will give us 0, 0, 15, 15, 0, negative 3. Plus 5 row 2 will give us 5 times row 2 will give us 0, negative 10, negative 15, negative 10, 5, and 0. Here's my result. 0, negative 10, 0, 5, 5, negative 3. That's my new row 2. If you notice, we're almost done here. But the only thing that's left, that all these numbers diagonally must be 1. So for example, I'm going to multiply 1/5 times row 1, negative 1/10 times row 2, and negative 1/5 times row 3. See? Negative 1/10. Right, so if I multiply negative 1/5 times row 1, that becomes a 1, 0, 0, 0, 0, and 1/5. If I multiply negative 1/10 times row 2, it's going to give us 0. It's going to give us 1, 0, 1, negative 1/2, negative 1/2, and positive 3/10. Then if I multiply negative 1/5 times every element in row 3, it's going to give us 0, 0, 1, 1, 0, negative 1/5. So this is my inverse. Let me go back. So the 0, 0, 1/5, negative 1/2, 3/10, 1, 0, negative 1/5 is considered my inverse. And I believe we're done with this workshop, guys. And again, I want to apologize for the phone call, but I was expecting a really important phone call and I had to answer it, and I apologize for that. Okay, let me go back and take it to the host so they can tell you more about what's coming up in the next few weeks.
Next week, we will have exam review 3. Thank you so much to Professor Albert Isasi for presenting today. Thank you to the audience for coming and being a wonderful audience, and we hope to see you again soon. Thanks.